Alright, well, hey folks, my name is Cameron Nixon, and today we're going to be talking about how to hodograph. This is a talk that I've given to a variety of National Weather Service offices, and I also had the privilege of giving this to the Storm Prediction Center. I kind of consider this as kind of a state of the science, so to speak, as much as how we could use hodographs to better improve the forecast process of severe storms. So, without further ado, what is a hodograph? Well, this is actually a question that I got wrong on my proposal defense because I said it was a plot of the wind with height. That is actually a plot of the wind shear vector with height. This is the line that connects each of these wind points. That is the wind shear. And so when you connect the dots, this is a big line that shows the shear as you go up into the upper levels of the atmosphere. So why is it important? Well, you may have heard in various discussions that organized convection is possible today. And what's doing this organization is the wind shear. This is what creates these storm structures. The structure is how a storm is organized. And so these are two supercells that I took photos of near the Illinois-Indiana border. And one of these produced a tornado, and one of these has produced a lot of hail. And if you've been a storm spotter for long enough, you could probably actually tell me which of these produced a tornado and which of them didn't. Even though they have relatively similar looks to them, they probably were in the same thermodynamic profile. You could see some low cloud bases in both. But the one that ended up producing the tornado was this top one here. And so this kind of just goes to show, especially if you were able to get this one right, that a storm structure is really indicative of its potential to produce hazards, right? If you're able to just look at the storm and give me a probability that each one produces a tornado relative to the other, that's some pretty useful information. But I also want to kind of hammer home the idea that it's not like this supercell here is disorganized. I hear a lot of people that like to say that a supercell might be disorganized because it failed to produce a tornado. That's not always the case. This is a really long-lived, hefty hail-producing supercell. And it was just organized in a different fashion, that it didn't allow it to produce a tornado like this top one did. And this can also manifest itself as reflectivity signatures. Folks in the Great Plains might know this tornado to be a supercell to be a more cyclic tornado producer, whereas this one tends to be a hallmark of the Southeast and produce a lot more long-tracked tornadoes. And you could tell that just based on this reflectivity signature if you've watched enough of these events. Which is pretty cool because you're able to kind of intuit all of this knowledge without even knowing what's going on. And what's going on is the hodograph is altering these storm structures. So what I like to say in this presentation is I call this a storm's behavior. This is how a storm tends to be structured and how it might even change its structure over time. You can see on the right here, we have a supercell on the top that really doesn't change its structure for a long time and holds on to this tornado for this entire period. Whereas the supercell on the bottom is really rapidly cyclic. It's changing shapes pretty much every frame you look at it. There's a lot of shape shifting going on. So how do we predict this? Well, in the most fundamental sense, the storm's behavior is governed by the storm relative winds that it feels. So this is kind of like if you're driving 60 miles per hour on a calm day, you're going to feel 60 miles per hour wind at your face. That's what you're feeling relative to the ground. So in this case, the storm's cruising at 40 knots, and it's going to be feeling about 40 knots of flow from the surface here. But these storm relative winds are induced by the storm's motion. So if the storm randomly decided to take a halt and stop right here, we'd really reduce our storm relative inflow here, and we'd really strengthen our storm relative outflow up here. So what's really important is that, yeah, this hodograph is really important. This hodograph shape is important. But if we move our storm anywhere along this hodograph relative to the rest of the shear, we're going to completely change its behavior, right? This storm here is going to be completely different than a storm that operates with this kind of motion here because it's feeling different things. And so this is really important because you could have a given hodograph on a certain day, but have completely different storm motions, regardless of what your storm is. So the storm motion then is determined by the wind profile itself for most cases, as well as external forcing, and we'll talk about that later. But what this means is that we can change, say, the upper level winds to be more westerly. That's going to drop our storm motion down to be more westerly as well. That's going to change your storm relative winds, and the whole thing is interconnected. So what we can do here is say that for most storms here, especially when there's not this external forcing, the storm's behavior depends on the wind profile. And what this means is that the storm structure depends on the hodograph structure. This is just a really eerie comparison between multiple, really long track, intense tornado producing supercells and then the hodographs that they're associated with. And I really want to convince everyone here with this image here that it's the shape of the hodograph that's doing this organization, this behavior making in these storms. Everything, every little twist and turn in here, all these little details matter going into this final result here. And when we're using the parameter space, then we're really oversimplifying what's really going on in the entire hodograph here. For example, effective layer shear, we're just taking 2 points along this hodograph. We're taking the surface point and then another point up above here. When we use this, we just need to remember that these bullseyes of effective shear, they're not exactly telling us much. We need to look at the entire shape of the hodograph. So first, I like to get folks thinking in terms of 3 dimensions when they're looking at these hodographs. So what you might see in this case is really strong shear, right? This is a crazy supercell environment. But I also want to draw your attention to the part of the hodograph here that looks pretty small and insignificant, but actually spans 8 kilometers worth of the atmosphere. So here is actually really weak shear throughout the entire depth of the storm almost. And this isn't great. This is kind of a moist tropical environment here that your storm's in. There's no shear throughout the entire depth of the cloud layer. And this definitely does have some detrimental impacts on supercell formation and maintenance. Whereas in this case, you might see a little bit more of a weaker shear hodograph, probably more marginal day. But once this stacks up, we actually have quite a bit of nice cloud layer shear for these supercell storms to sustain themselves. And so this is a pretty good hodograph, especially for more rapid development of robust storms. So we kind of work ourselves into a paradox when we use this effective layer shear here then. Whereas we just generalize that more shear is better. And that's not always the case. Our bullseyes of effective shear might actually be giving us a little bit more of a junkier hodograph that really doesn't sustain as strong of a supercell as this one does. And that this hodograph might even fly under the radar if we're only looking for, say, a threshold of 35 or 40 knots or so to get strong storms. We're not even going to really see this one. So it's always important to look at the entire profile as a whole. Stronger shear really doesn't always give you stronger storms. So the shear profile is really important and all. But remember, storm behavior is governed by the storm relative winds that it feels from that shear profile. And that can vary for each and every one of these storms that's moving in every single which way in this loop here. And so I like to kind of partition my storm motions into 2 varieties, so to speak, free and forced storm motions. So let's talk about free storms first. These are storms that move with the mean wind. They're kind of allowed, they're freely allowed to move wherever the wind carries them, so to speak. They don't have different aspects of the environment tethering them down or forcing them to move in another direction. They just blow along how the hodograph would kind of govern them to move. And so in this case, we have updrafts that initially start moving with the mean wind. And I'll stop right here because this is an important concept in itself. Because oftentimes I see folks trying to predict supercell formation or whether or not a supercell is going to form using SRH. And you might say, oh, we got 300 SRH today, so we're going to get supercells. But in doing so, we're actually working ourselves into this logical fallacy because we're already assuming a supercell exists. And we're using bunkers right, which we don't actually have this yet. We have a mean wind mover. So in my experience, it's generally better and more logically sound to use the hodograph itself to predict whether or not supercells are going to form, especially since you're neglecting the crosswise component as well when you just look at SRH. And that crosswise vorticity is pretty important in supercell development, as we'll talk about later. But once these things start getting their mesocyclones, they can deviate from this shear vector. And this is the bunkers technique, where you draw a shear vector in the cloud-bearing layer, and then you deviate from that shear vector 7.5 meters per second on either side. So this is a real-world example of this working, where you have a splitting supercell pair, just a gorgeous mirror image display here. But they're gonna deviate from that shear vector on either side. And so what we're dealing with here is what's called linear dynamics. And without making this complicated, all we're doing is looking at the distribution of high pressure and low pressure on either side of the storm caused by the updraft interacting with a vertically sheared environment. So when we have a shear vector that, say, points easterly, like this case, we have a high pressure on the up shear side and a low pressure on the down shear side. So we're actually going to induce rising motion where these lows are, especially if we go from higher pressure to lower pressure. We're going to induce a rising motion here and a sinking motion here. And you can see that the sinking motion and the rising motion, neither of these are actually co-located with this cyclone and this anticyclone. But when we have a curved hodograph, we actually do get that co-location. We have a high pressure below a low pressure, which is going to induce a lot of rising motion along the southern flank of the storm, which is how you get an enhanced right-moving storm here, because your rising motion is going straight through this mesocyclone here. Whereas where we have our anticyclone, or left mover, we have a lot of sinking motion, and that's literally going to squash that left mover to the point where it really can't sustain itself as much as this right mover. And so what we need to remember is that not all of these right movers actually turn right. This term is kind of a misnomer, but we need to remember that it turns right with respect to the shear vector, not with respect to the ground. So in this case, especially in the southeast, where you have a lot faster storm motions, you end up still having a deviation, but it's just not going to be very noticeable because you only change trajectory by a few degrees. Out in the plains, especially late spring, summertime, you might get scenarios like this, where you have an updraft that initially moves northward, but once it acquires a mesocyclone, it just parks it right in the center here, and this can lead to a variety of flash flood tornado hazards. But my favorite example is this, where you actually have an updraft that initially moves off to the northeast, and once it acquires a mesocyclone, once it turns right, it actually turns left with respect to the mean wind. So you actually see this storm backing up and hooking up to the left once we establish a right-moving mesocyclone. So this is really paradoxical, and I assure you this doesn't happen very often, except for especially in the vicinity of hurricanes. But this does happen, and you can get leftward turning supercells that are right movers. But the thing about supercells is that once you deviate, once you become a right mover, you have access to more SRH. You have access to more streamwise vorticity and typically storm relative inflow. So these are both very good, as we'll talk about later, at sustaining the storm. So this is why we get some pretty robust right movers in the US, is because they're favored and they deviate to a position which gives them a lot more kinetic energy from that hodograph. Wider storms actually deviate more. This was a concept brought about way back, and really hasn't been looked at since. But this is something that dynamically checks out. You have broader updrafts like this one that tend to be at their most intense when they're most rightward deviant. And then you can compare this to, say, this mini supercell that occurred about the same time frame, interacting with the same hodograph, but we're actually deviating a lot less. We're moving more northerly, just because we don't have a broad enough updraft to interact with the shear profile the same way this one does. And it's also been noted in very recently that tornadic storms might actually deviate more than non-tornadic storms. So this is a signal That's coming out of these cases that might be important to look for in, say, warning operations. Tornadoes actually also have motions of their own. We've noted for a while that tornadoes take these left turns at the end of their life cycle, and this is a really cool case just west of Salado, Texas, where you had a tornado initially moving almost due east, and then just looks like it hit a T intersection and had to go one way. And this is exactly what happened. It moved due north. And so what we've noticed is that these tornadoes actually detach from their parent storms at the occlusion. And so you can see in this case, our parent storm, our sculpted mesocyclone here, this is going to be moving with bunkers right, or with all the linear dynamics that we were talking about earlier. But you see this big rip here. The tornado literally separated from its parent here and is off just kind of left to do its own thing and flounder around in whatever flow that it's going to be in. So what naturally affects its motion is the low level wind. It's the wind that the tornado just kind of put itself into. So in this way, we actually devised a technique where a tornado motion, once it occludes, is actually the average between the low level mean wind and the right mover from which it initially came from. So this is how you can get weird cases like this, where your right mover moves down south, and your tornadoes spin off to the top here. Because they're guided by this low level flow once they leave their parent storm. But those were all our free storm motions. Those were storms that were allowed to move the way the Hodograph intended them to move, so to speak. Forced storms don't do this. They don't play by the rules. They have a motion that's governed by some kind of external forcing. And so one example of this would be storms or supercells on boundaries. These storms move with the boundary. They're tethered to this boundary that can do its own thing if it wants to. These storms can anchor and then even zipper down like this one does to the southwest once it gets a strong enough cold pool to propagate the storm downward. And so the thing about these forced motions, these boundary motions, is that the supercell moves in a way that really is not predictable using the Hodograph. You can't predict this westerly motion here with the shape of the Hodograph alone. We need that information. We need the boundary. Storm mergers as well. The motion after these mergers depends on the combined impacts of both of those storms, and perhaps even a temporary widening of the updraft here once it merges. So in this case, you have a few supercells that merge together, and you can see the supercell just parks it here, and then begins, once it sheds all those mergers, it starts becoming a little bit smaller and deviating a little bit less at the end of the loop. But these merging cases, we cannot actually predict their behavior or their motion using just the Hodograph. We need the information that this storm is undergoing a merger. Convective systems move a few different ways. Each of their individual little counterparts here move with the mean wind, but the system as a whole actually can move toward the low-level jet. This is the case of the Corfiti upwind propagating MCS, because they actually move toward the convergence caused by the low-level jet. Or they could move with the added component of the cold pool strength. So if we have stronger cold pools, we have MCSs that move a lot quicker relative to the mean wind, like this derecho does. But what I really want to hammer home about all these forced storms is that if there's external forcing, the Hodograph by itself cannot predict the motion or the behavior of these storms. We need that motion. We need that information from the motion. And we should always use observed storm motion when we can. One example for this is I tend to see folks using, say, SRH to predict mesovortices in QLCSs. And when we're using SRH, 9 out of 10 times we're using this bunkers right moving SRH if you're looking at a map of SRH. And this is irrelevant. This doesn't actually matter in this scenario because we're not moving to the right. We're moving wherever this system is moving. So we need this information. So for the meat of this presentation, we want to look at the Hodograph as it is felt by the storm in the storm relative sense. So all we're going to do here is take a classic ground relative hodograph, and we're going to subtract storm motion from it so that the storm goes to the origin and that the rest of the hodograph goes down here. So we're going to do the U and V of the hodograph minus the U and V of the storm, and then you get this. We just translated this down to the origin. And what's really cool about this is now we can actually see exactly what the storm is feeling. The storm is feeling 35 knots of storm relative inflow here, 10 knots of storm relative wind here, 35 knots of outflow up here. The storm is feeling all of this. And we can compare and contrast these to a lot of other cases as well to see how those storms operated. But there's two main properties of the storm relative wind that can really be deduced from this storm relative hodograph here. And the first is the speed of the storm relative wind. And when we're dealing with storm relative wind, we're typically used to dealing with outflow. Or we've probably used anvil level SR flow or some kind of SR flow aloft. Because this actually regulates the ventilation of precipitation out of your supercell. So when you have strong storm relative outflow, you get more lower precipitation supercells, which are a lot easier to see and spot because the rain is not pounding into the action area here. Whereas when we have weaker storm relative outflow aloft, say this case less than 20 knots, we get big HP beast storms. And this is these are really difficult to spot, and these can also generally lead to some pretty messy storms as well, as they're forced to kind of inhale all of their precip that they just dumped in amongst themselves. But you could also veer your storm relative outflow all the way around your storm motion like this. And this is how you get these big, icky fishhook shaped supercells that are often found in the southeast that quite literally rain into their own forward flanks here, and then they move into that core. So these are pretty messy to spot. But when you back your storm relative outflow around your storm like this one, we actually end up with a much smaller sliver where that storm relative wind is preferentially blowing. So all your storm relative wind, all your rain, ends up blowing off to the north here in this small little sliver as well. So when you have backing aloft, this actually gives you much lower precipitation storms usually that aren't actually raining into their own trajectories here. And they're a lot easier to spot if you sit out here. But we're a lot less used to dealing with this concept of storm relative inflow. And this is something that has really only taken off in the past couple of years, but shows a lot of promise in being able to diagnose and understand potential storm morphologies. And because what storm relative inflow does is it regulates the mass flux or the moisture flux into the thunderstorm. And so this regulates the storm's size or the updraft size. So when we have stronger storm relative inflow, like in this case, we actually have 35 or greater knots here throughout a deep layer. From 0 all the way to 1 kilometer, we have greater than 35 knots, and that's pretty strong. And so what this does is just induce bigger supercells. This was the famous Hondo, Texas record hailer case back in 2021. And it was birthed by a really big supercell in an environment with really strong storm relative inflow. So this is the kind of hodograph that encourages these big plane style supercells. Whereas when we have much weaker storm relative inflow, say this case is only pushing about 20 knots or so from 0 to 1 kilometer, we really don't have enough mass flux to sustain a big supercell, which is why we typically end up with these mini supercells. And these cases can surprise some forecasters, where we still have strong enough SRH here to support mesocyclones and tornadoes, but our storm relative inflow is just weak enough that we don't get these big classic size storms. And these can fly under the radar in terms of convective allowing models as well. So it's really important to be able to recognize an environment supportive of mini supercells and then assess accordingly. But the second component then of our storm relative wind is its spin. And so this is a product of shear vorticity. And so what happens here is we have a rolling motion in the atmosphere due to our shear, and it's going to be proportional to the strength of the shear. So when we have a much stronger shear vector here, like we do in the low levels, we have a longer vorticity vector. We have more vorticity. And then when we have weaker shear here, like when we do between 1 and 2 kilometers, we have a much smaller vorticity vector because we just have less vorticity. We have less of this rolling motion. And so this is actually perpendicular to the shear vector here, this vorticity vector is. And this is due to the right-hand rule, and essentially this is to the left of the hodograph as we go up here. But what matters then, this is the vorticity you see here that's felt by the ground. But what matters is the vorticity felt from the storm here. And so when we have a storm relative wind that blows through these vortex lines, envision this as kind of a line of vortices from the east to west here. When we have a storm relative wind that blows through this line here, this is going to quite literally rotate our storm relative wind. Our storm relative wind will rotate. And when our storm relative wind rotates, our updraft will rotate as well. And so this is how you get immediate updraft rotation. And so this is also how you get a mesocyclone that ends up pretty perfectly co-located with your updraft as well. This is the case in these mothership supercells where it just looks like the entire storm is rotating. The updraft is the mesocyclone. Everything is kind of rotating in unison. Whereas when we have a storm relative wind that flows across this vorticity vector here, this is actually not going to induce updraft rotation. This is going to induce rotation along the flanks of this updraft. So it's kind of hard to envision, but your updraft is not actually rotating, but it possesses rotation along the flanks. It's almost like if we had a vort max along the side of the storm. It's not rotating, but it is feeling rotation. It does have rotation. And so what this does is actually something called nonlinear dynamics, where we have rotation in the atmosphere, and that is going to induce rising motion. So now we have an updraft, which is obviously rising, but we also have rising motion along the flank of the storm. So this updraft is going to want to propagate toward this because it wants to move toward the rising motion. So when it does this, both sides do this, and then we split. This is how we get splitting supercells. And our classic mirror image right mover, left mover pairs here. But this is just going to continue until this updraft just keeps attempting to catch up to this upward rising motion here ahead of it. It's going to continue propagating in this way due to the crosswise vorticity. And this actually manifests itself as kind of a battleship supercell structure, I like to say, because this is a lot more elongated and there's a lot less obvious signs of rotation. It's not that big round spaceshipy looking thing, but it's actually kind of hard to tell that this updraft is even rotating here. And that's likely because most of its rotation is confined to the flank of the storm. You can see some dust being kicked up. This was actually where I almost witnessed a tornado form. But this just goes to show you that the orientation of vorticity, the streamwise versus crosswise, has a lot of impact on the structure of the storm itself. So when we're forecasting then, we want to quantify the vorticity in the atmosphere, and there's two different ways we could do that. The first is how much streamwise vorticity is there in the environment. And so when we're talking about how much, we're talking about a magnitude of vorticity. And so we typically just call this the streamwise vorticity. How much streamwise vorticity is there? And streamwise vorticity literally governs how strongly the updraft will tend to rotate. So if we inject more streamwise vorticity in the environment, given that same storm, it will rotate stronger. And this is estimated by the storm relative helicity. And what this is the area underneath the curve here of this hodograph in the effective inflow layer, especially. So it's swept out by the storm relative wind at the surface to the storm relative wind that we cut this off at, which is usually the effective inflow layer top. And it's this area between the right mover and the hodograph here. But what we need to remember is that SRH is only an estimation of streamwise vorticity. It's not actually streamwise vorticity. It's a product of both the streamwise vorticity and the storm relative inflow, which we've learned does completely different things. And so we work ourselves into this paradox that we think that intuitively more SRH is going to give us more updraft rotation, but that's not actually always true. In this case, we actually increase our SRH here, while we decrease our streamwise vorticity. We increase the area of our triangle here, but we actually decrease the length of the shear vector. And what this means is that more SRH really isn't always a better thing. This doesn't actually always mean more streamwise vorticity. In cases like this, might have a lot more potential even to produce tornadoes than this case here, even despite its weaker low-level SRH. But the second way to quantify the streamwise vorticity is how streamwise is this vorticity. So this is a measure of how purely the updraft will rotate. Will we be rotating purely, or will we have kind of a vort max like we talked about earlier? And this is estimated by the critical angle. And I personally think that there's a lot of utility in assessing the streamwiseness aloft, especially say 1 to 3 kilometers or so. But what critical angle does is estimate the streamwise vorticity in the lowest 0.5 kilometers because we consider this to be most important in the tornado process. And so unfortunately, critical angle, it basically, the goal is to quantify or to describe the specific shape of the hodograph that ideally leads to more streamwiseness. It doesn't actually estimate streamwiseness itself, nor is it meant to. And so what we get here is this imperfect relationship between, we compare the storm relative wind at the surface to the shear vector in the lowest 0.5 kilometers. So we're comparing it to this vorticity vector here. So we're not actually comparing apples to apples here. We're comparing apples to oranges. And so what you get is this another paradox where you can actually get purely streamwise vorticity here, even with really low critical angles. Because we're not actually looking at the same thing. Critical angle is looking at the shape of the hodograph, but the shape of the hodograph in this case really doesn't actually govern tornadoes like we think it does. What really matters here for tornadoes, at least, is the purity of the streamwise vorticity. How streamwise are we? And that can only be assessed with streamwiseness. So critical angle really doesn't have to be 90 to have pure streamwise vorticity. And I've noticed this happen, especially out in the southeast US, to a lot lesser degrees than this. But we can still end up with cases where we have a critical angle, say, of 60 degrees, and it still be very favorable for pure streamwise vorticity ingestion. So for supercell storms, we're taught that they need SRH, right? This is kind of a no-duh statement. We need to get a rotating storm, we need SRH. But this isn't actually always the truth. What also matters here is crosswise vorticity, right? We can still make a supercell that has rotation with crosswise vorticity only. There are many cases where we actually can get a supercell to deviate in a fashion that really only gives it a very negligible amount of streamwise vorticity. So it's existing in almost purely crosswise vorticity. We can even get a supercell that's born in streamwise vorticity, but then the hodograph changes and now it's stuck in crosswise vorticity. That doesn't exactly mean we're going to die. That doesn't always happen. And this was one case where we had a pretty negligible amount of streamwise vorticity throughout much of its life cycle. And we just know that this crosswise vorticity can dynamically help sustain supercells. So we can get supercells in environments with crosswise vorticity. And vertical vorticity should always never be discounted. This was the infamous Gerald, Texas case, where we can really bend this up and say that we had negligible low-level shear in this case for the Gerald case. For as much data as we have gotten from this event, it's more than likely that the storm was ingesting at least 90% of its vorticity, its potential for updraft rotation from this boundary that it propagated off of. So what I'm really trying to say here is that SRH really is only half the picture, right? If you're looking at plan view maps of SRH, or if you're using supercell composite, what we're ignoring is the fact that supercells can also be sustained with crosswise vorticity, and crosswise vorticity will add to the overall intensity of those storms because this is still vorticity, and we're also ignoring vertical vorticity. So SRH will not tell you this, and this is why we can look at maps of hodographs, and this will actually alert you that this is a very favorable environment for supercells, even though we're barely pushing above 100 SRH. So what about Veerback then? There's this prevailing myth amongst chasers and forecasters that Veerback somehow suppresses the mesocyclones of these storms. And going over these linear dynamics earlier, there is actually a way that we can get suppression from this linear dynamic term. It's mostly confined to instances where we have a shear vector that backs aloft well over 90 degrees. Like in this case, we back aloft over almost 180 degrees. So we will have some suppression due to that linear dynamic term. However, the net result that this process leads to a net result of suppression really is not always going to happen, and usually really isn't the case. We also have to consider we might have an intense amount of SRH here near the ground. We might have extreme buoyancy. We might have all these things that outweigh the subtle impacts of these linear dynamics suppressing these mesocyclones. We also have to consider cases where most of this backing is aloft, which really especially is not going to have that much of an impact on the mesocyclone itself, and cases where we just have, in this case, less than a 90-degree angle. This isn't even going to end up linearly suppressing the storms to any degree. And especially when our shear is really weak in this layer too, right? That's also not weak shear in the layer. It really is not going to contribute to a large suppression. So cases like this, if you see anything remotely close to this, we really are not dealing with a case where suppression is going to be anything more than negligible for these supercell storms. And I think the most important thing that we need to consider is that recently research has came out with other things that this bagging aloft can do that might actually work to enhance a supercell. So especially this Gray and Frame study found that bagging aloft actually really increased the frequency and the longevity of tornadoes in their simulations. And there are a lot of cases just observationally that have produced really long track tornadoes with backing aloft. There's thoughts that it might help redistribute the downdrafts of these storms in a way that allows them to better kind of sustain themselves without reining into their own updraft and stopping the tornado process. So when all is said and done, the net impact of this backing aloft typically is not, or overwhelmingly is not, going to suppress the mesocyclone in any meaningful fashion. Really, in fact, we should be considering the opposite hypothesis now, that backing aloft might actually have a net strengthening effect, as both of these studies have suggested to us. So hazard type then, this is, as we're finding lately, kind of actually a low-level shear problem, both for tornadoes and for hail. And so for tornadoes, most of us know who are watching this that we need a robust low-level mesocyclone. We need a strong supercell. And this is going to need a lot of low-level streamwise vorticity to get the job done. And the streamwise vorticity can be provided by the low-level shear, which is why in this case, when we plug in all of our cases here and get the average hodographs of each, we find that our weaker tornado cases have the weakest low-level shear, and then once we go step up to our violent tornado cases, we're just adding low-level shear. That's the main discriminating factor between these samples. So it shouldn't be any surprise then that low-level shear is good for tornadoes in most cases. But for hail, we need to look at a completely different process. This is a very different problem. This is not as easy as saying, okay, we need a stronger supercell to get stronger hail. This is based on a couple things. We need a sufficient amount of embryos within the hailstorm, which are essentially little baby hailstones. And we need a sufficient amount of residence time of these hailstones within the updrafts to grow. And so, what we need for this residence time aspect is we need to keep this hailstone aloft in this hail growth zone for the longest time that it can. And this hail growth zone is this favorable temperature region in the atmosphere between -10 and -30 degrees Celsius. And it's actually in the mid levels of the atmosphere. It's not at the upper levels. We're talking around 6 kilometers or so is where this hail is most favored to grow. And so what we need is an updraft that's broad enough and weak enough to keep this hailstone within this hail growth zone for as long as it can. And if once the stone lollygags for long enough, it might actually grow to a pretty sizable size. Um, so what we need here is a lot weaker shear, both for the aspect of weaker shear that typically gives you stronger storm relative inflow, which is going to give you broader updrafts, and weaker low-level shear is kind of going to cut back on your mesocyclone dynamics, right? We don't want a really robust, intense mesocyclone usually, because when we do, our hailstones go straight up through the mesocyclone, spend 30 seconds in the hail growth zone, and are immediately catapulted out into the anvil here before they have any time to grow. So low-level shear really is not the greatest for this process. And we've also seen that low-level shear can lead to advections that kind of spit these hailstones out of this embryo curtain prematurely as well in the horizontal. So in this case, when we have stronger shear, our hailstone is kind of ejected out of the embryo curtain before it has time to lollygag through this embryo curtain toward the hail core here. So it shouldn't be a surprise then that when we composite all of our hail hodographs, we find that all of our samples, both our small hail and our large hail samples, feature weak low-level shear. And that's kind of the distinguishing factor of storms that produce hail, especially compared to our tornadic storms. Because all those processes above, like I mentioned, are disrupted by this low-level shear. And so we kind of have this potential spectrum of events where typically the case on the left here, where we have weak low-level shear, is very favorable for hail, but it's very unfavorable for tornadoes because we don't have much streamwise vorticity here. But on this case to the right, we have strong low-level shear. This is very favorable for tornadoes, but it's also not favorable for hail because the reverse is true. This low-level shear typically disrupts the hail process in a lot of cases. But what about elevated storms? When we look at whether or not a storm is elevated or not, what we're talking about is the effective inflow layer and where that storm is kind of rooted, what kind of air mass is in its inflow, so to speak. And in most cases, when we have surface-based storms, our effective inflow layer is quite literally at the surface here. We are ingesting near-surface parcels. But let's say our effective inflow layer was aloft here. So you're probably above an inversion. Maybe your storm crossed north of the warm front, and there's now a very stable air mass that we really can't be pulling much from. So in the case of elevated storms like this one, these are going to be based above this strong low-level shear here. So if we kind of just ignore this shear now because our storm really is not feeling it that much, we're going to change our predominant hazard type to hail. And we're going to be favorable for hail now because we've effectively reduced the low-level shear that the storm is feeling in its inflow, which is going to make it more apt to produce hail now, even if it wasn't apt to produce it before. And we always have to remember our forced storms and how these can lead to major caveats within the conclusions that we talked about above. When we're dealing with storms that are on boundaries, storm mergers, like in this case, or anything related to convective systems, this is going to change the behavior of the storm such that it's not exactly predictable by the hodograph. The hodograph itself cannot predict storm behavior, especially in the case of forced storms. Especially there's many instances where, say, you have an environment that's mostly favorable for hail, but not tornadoes, and you get a cell merger and you get a tornado. Or you can have an environment that's mostly favorable for tornadoes, like this one. You get a merger. You can also get hail with this environment. Or if you're in an MCS that happens to move in a particular direction relative to the hodograph, all sorts of things can help induce hazards where otherwise were not predicted using the hodograph. So always be wary when you are dealing with cell interactions like this, or other things that force a storm's behavior, such as boundaries or convective systems. So last but not least, I will chat about the benefits of using the Hodograph maps on a variety of sites. This one from the SVC mesoanalysis actually has the effective inflow layer plotted. So you can do the kind of effective inflow layer analysis that we were just talking about, where both of these hodographs here you can see are pretty unfavorable for hail growth. But if you see this case, we have an effective inflow layer based upon the surface, but north of this front here, we have an effective inflow layer based above, say about 0.5 kilometers or so. So in this case, we're kind of just going to mentally ignore the shear profile below here. And we can see that we have a relatively long and straight hodograph with weak low-level shear. And so that's going to be very good for hail production, and that's what happened on this day. COD also has some pretty awesome storm relative hodographs. So here is the only site where you can actually see this hodograph in the storm relative sense. So you might be able to say, okay, we got really weak storm relative outflow here at loft, so any supercell that forms here might be particularly high precipitation. And then Pivotal Weather just has an amazing array of hodograph maps for pretty much any model. Even the convective allowing models, I was initially a little bit hesitant about that because convective allowing models, the signal can obviously be altered by convection. But after looking at enough of these, I could pretty much say that the convectively induced changing of hodographs is A, pretty cool to look at, and B, not always really a problem while you're forecasting. It's usually pretty obvious to tell if a hodograph is being smacked by some MCS or something. So definitely recommend their site. I'll also plug Tim Sapini's VAD wind profile page. This is just a really cool way to look at observed VAD wind profiles from our WSR88D network. So if we, in this case, we're looking at the BMX radar out ahead of a really long-tracked, intense tornado-producing supercell. And we can even take this in the storm relative sense, so we could apply all the concepts that we were talking about today, right? We got really strong storm relative inflow, we got strong outflow. This is probably going to be a big supercell that has pretty nice ventilation aloft. We also have a pretty large streamwise component in the low levels and lots of streamwise vorticity in general. So we're probably dealing with a pretty intense tornado threat, and that's exactly what happened. We could also compare cases like this to cases that I've archived at the ustornadoes.com/case archive page. There's a lot of really cool cases, both from a forecasting and historical perspective and to a storm chaser perspective, just showcasing a lot of different hodographs and SKUTs that you can get for some pretty impactful or just otherwise interesting and photogenic events. So with that, I thank y'all for watching. I hope you learned something, and happy hodographing.